Uh, I don't know what you mean from 1 to 9. No, it's the ones that are on the announcement. I don't know if you saw I don't know if that's what you were asking. There's this announcement about the quiz problems. Is that what you're asking?
Yeah. So these are all the possible questions that will be on the quiz, right?
Correct. Yes. But there are only 7 problems. Yes.
Yeah. So
So it's
so
not.
so so the quiz tomorrow has 7 problems.
No, it's 2 problems. It's just that they are based on these 7 problems.
Yeah.
It's just based on these problems that's what the quiz will be based on.
Okay.
But yeah, like 7 problems would be too much. It's just going to be one of 2 out of these 7.
Yeah.
It's just right. It's not ordered, so it's not the PDF is kind of like, I mean, it's kind of organized by topics, but not, since I have added them over time, they like it's not, you don't have to go through, you shouldn't begin at problem 1. Like it's more like based on these ones. Yeah.
Yeah.
They have the solutions also. Did I push the solutions here? Let's see. Oh yeah, they have the answers. Like because some of you had asked me about that yesterday. Let me see. Oh, then maybe before I do that, so I also did create yesterday. There is an assignment, or I mean, not even an assignment, like called more like a responders test. It's just for you to practice responders because the quizzes we will use responders to take the quizzes just because that's what we will use for taking the exam. Um, uh, so yeah, I mean, this one is not graded or anything. It's just for you to download responders, make sure it's working. So just try it out before tomorrow because sometimes, like, depending on what computer you're using, or it can be kind of it can give you some problems, but yes. So just try it out if you haven't before yet. No, it's not open notes. But it is the same problems as it is copy pasted from the problems I give you on the announcement, so it shouldn't be any surprises. But it's not open notes because I mean the exam is not open notes, so but yeah.
Professor,
Mm-hmm.
I had a question on one of the problems that you gave
Uh-huh.
for the quiz. So it was problem number 48.
Let me check it. Just 2 questions. 48. Yeah.
So it said here that only 3 would be the only solution, but 4 is like the same thing as the extension of the or the expanding of that formula, right? So would it be 3 and 4?
Oh, I may have. Do you think? I may. But also it says. Okay, yeah. Even the solution says 4 works. So
Oh,
okay, no, but I probably wrote it a slightly weird way.
hmm. Uh,
Yeah. So my mistake, but yeah, it says 4 works. So yeah, probably I just should have written the solutions in a slightly different way. Yeah.
okay.
Is that the one that you? Yeah. Although that one, like, it's with my matrix multiplication, and we still have to say some things about matrix multiplication.
And then
Today.
I had a question on 49.3. Oh,
Yes, I see it. Yes.
so for 49.3, I was wondering, is this in the absolute sense like it has to be a square matrix, or is it like it can be one? Since can't AB and BA also be like of different dimensionality? Like,
Well, we can do it after we talk more about we can do it in class once we discuss like how to multiply matrices of different sizes.
okay,
But yeah. It depends. Like we can. That's like a good problem to go over, but
Mm.
it's not. Yeah. I still need. I still haven't only done the 2x2 case today. Yesterday, so I still have to say like a little bit today about how to do the multiplication in the general case.
okay, sounds good.
Let's see. Yeah, so today, okay, so the first thing I need to tell you today is like a useful way to do the matrix multiplication. So for that, we do have to talk first very quickly about the dot product. I won't say almost anything about, I would say very little about dot products, but it's just essentially the minimum stuff that we need for like carrying out the matrix multiplication in a better way. So let's talk about dot products. Dot products is a way to multiply vectors. So this is like a way to multiply way to multiply vectors. Two vectors with the same number of entries. That's important. And obtain a number. Number is the result. So it is like a very easy operation. It has a lot of applications and useful things, but we won't use those until the end of the course. So for now, I'm just giving you like the formula because that's all that we need. Like you can start with an example of what it is. So let's say that you had a vector of, let's say you have two vectors of two entries, U and V. So let's say you have these two vectors. Okay, so what's going to be the dot product between them? Notice that it's called dot product, literally, at least for us, because there is a dot in the notation between the two vectors. So there's like you see a dot here, and that's why it's called dot product. So the name is not too like there's nothing too suspicious like about the name. It's pretty straightforward name, just because like the symbol itself uses a dot. Okay, so again, it's kind of a way to multiply the vectors together. So essentially the way to I can copy them again. So this is what the vectors are. And the idea to do the way in which the dot product is supposed to work is like what basically you just multiply the corresponding entries and add them together. So you multiply this entry with this entry. So that would be give you let's put them in in red. So yeah. You multiply this entry with this entry, so you get 2 times -1. And then you multiply this entry with this entry. So the first entries get multiplied, the second entries get multiplied. And then you just add up the result. So that gives you -2 plus 12, and that gives you 10. So it's kind of like just like level multiplication at the same height, and just add up all the multiples that you get. Well, it depends on what you mean by the word order. In this case, this will be the same as v.u, if that's what you mean by order. So is that what you were? Yes, exactly. Yes, that's correct. So u.v is the same as v.u because it's the same. I mean, you can right. You can like since it's just it's just like a bunch of ordinary multiplications. So yes, these are allowed to change in order. Yeah. Then this one is this 4 times 3. Right, it's just because like the individual, right, like you can flip this order and you can flip this order, so that's why the overall numbers remain the same, right? So it's still -2 plus 12, which is 10. So in general, I mean, I was starting with I wanted to start it with some specific numbers, but in general, what that means is that if you take, like if your vector had 2 entries, which you can call x1 and y1, your second vector has 2 entries, which you can call x2 and y2, right? Then u.v which is the same as v.u, so I can also write that down. It's the same as v.u. Is just what we were discussing. So it is the first entries together. So you get x1, x2 plus the second entries multiplied together. So you get y1, y2. Okay, is that making sense? So that is what's called the dot product. Again, like it does have a lot of useful properties. Like there are actually many things you can do with the dot product. It's just that we are going to do them we're going to do those things later on. Right now, I'm just giving you the formula, but there are many. I mean, the dot product is really like a very useful operation. Like it can be used to find the length of a vector. It can be used to find the angle between two vectors. Like it can be used for many, many different things. It's just that those like applications of the dot product, we will discuss like later on in the course. That's one of the last topics in the course. So for now, it's kind of like just like operation that I'm giving you. It's maybe not too clear why is it useful, but you'll see just like kind of naturally appears on the stuff that we have been doing. The other thing is that it does like, I mean, the generalization is pretty straightforward. If you have vectors with more than 2 entries, which we haven't used so far, but like you can. So for example, like it generalizes to vectors or more entries in the same way. Or it generalizes to vectors with more entries in the same way. So for example, like again, just to start with something basic. If this had been U, and now this is V, and you can put a 0. There's nothing wrong with putting a 0 there. As long as they have the same size, as long as they have the same number of entries, you can do the dot product. So what would be in this case a dot product? Again, like level 1 with level 1, level 2 with level 2, and then let's use a different color. Level 3 with level 3. What does that give you? 1 times 3 gives you 1 times 3 plus 2 times 0 plus -1 times 4, right? Is that making sense? So that gives you what? 3 plus 0 minus 4, and that gives you -1. Is that okay? Is that making sense? Are there any questions about this so far? It depend. You mean like about in this particular operation, or? So that is not something we're going to use really in this class. Like there is a way called the cross product, but what I mean, there are a couple of ways you could do that. Like one is the cross product that works when the vectors have like 2 or 3 entries, which for many applications that's enough. So if you take like multivariable calculus or even like a physics class, we will talk about the cross product. But in linear algebra, the only type of, for this course, like the only type of multiplication that we need is the dot product. But yeah, there are other ways to multiply vectors if you wanted to get a vector instead of a number. But for us, the only thing that we really need is to take 2 vectors and produce a number. So that's the only thing that we need. Well, I don't think the transpose of the matrix, it would, I wouldn't need to, I don't think that any of the questions that I gave of the announcement used the matrix transpose, so I would say no. I also, yeah, multiplying two matrices, probably yes, but again, like you can check on the problems that I gave. Well, so it depends, is, oh, you mean like why we're using the dot product only? Or about the focusing on 2 variables instead of multiple? No, it has like the fact that the dot product is being used here is not it has nothing to do with the number of variables. You'll see in a second that for when we talk about matrices of bigger size, like the dot product will also be useful. So it's not so much because the vectors have 2 entries. It's just that the dot product is what appears when you are computing the dot product is the operation that you need to use when you're computing the the multiplication between matrices, and that's regardless of their size, basically. So I probably, well, I could do like a 3x3 example or something like that later on, but or a higher. I'll do some examples with different size today so that you see how it works. But it doesn't have. It's not specific to the fact that we're focusing on 2 variables. It's just it's easier to start with 2 variables, but. But yeah, like, so the formula, like for vectors with the 3 entries, again, it's really what you would expect based on what I have said. So you really would just take this as x2, y1, y2, z2, and then it's kind of like a level-wise multiplication, which just gets added together. So you can put here these ones. And then you can put these ones here. So u dot v is still u dot v. So x1, x2, y1, y2, and then c1, z2, and then you just add up the answers. Is that okay? And this can keep going. So like, I don't want to keep writing like the formula in the general case because it's exactly the same. So just like I'll let you do this example and then you can tell me what the answer should be. So let's do this. Okay, so what would you say the dot product is in this case? What number should you get? Okay, let's check it out. I haven't actually tried it. So this one with this one, right? And this one with this one. This one with this one. And then, yeah, we can use this one with this one. Right, so you get, I'll stop using the colors just to save me some time. 1 times 0. Okay, let's check it out. 1 times 0, 2 times 1, right? Plus -1 times 3 plus 2 times 5, right? Is that making sense? So this gives you 0 plus 2 minus 3 plus 10. Yeah, so actually, yes, 9. Good. Perfect. Is that okay? So you see, I mean, if the vectors had 10 entries each, you can still do the multiplication. It's kind of just taking more time. Oh, someone was going to say something, or was there going to be a question? No, like the formula is always the same. You multiply entries of the same level and then just add them together. That only requires you the vectors to have the same length, right? Or size, because if one vector has like 2 entries and the other 5 entries, then how do you match them together? So except for that restriction that the vectors must have the same number of entries, like the operation is more or less straightforward. It can be a little bit tedious once the vectors have like many entries. We'll get there in a couple of minutes. Yeah. We're warming up. I just wanted you to have like the formula for the dot product first, because it's just a convenient formula to have. for what I'm about to say now. So here's like the first thing that we can do with this. So again, like you should think for now, you should just think of the dot product as a useful way to memorize certain formulas. And that's it. Like later we'll use the dot product for other things, but for now it's just like a convenient way to memorize the things we have said about matrices. So for example, here's some like so the dot product formula is useful to memorize. It's useful to memorize other formulas. Memorize volume matrices. Oops. So let's start with the first formula that we had talked about before. So here's like the first formula which is like a matrix with a vector. So I don't know if you remember this, but which we have been doing before. So if you had like a vector which was xy, right? We were talking about matrices. So think of the matrix A as being like A, B, C, D. Okay, and that gives you out I don't know if you remember this. I gave you A, B, C, D. So X, Y, X, Y. Right. So I don't know if you remember this. You mean this purple box?
Yes.
Oh, it's just like a diagram for the matrix, because remember that the matrix, you could think of some machine that turns one vector into another vector. So it's just like a way to represent the matrix.
Yes. So what you're doing here is it's like you are multiplying a matrix by a vector, right?
Right. It corresponds to exactly the same that we were doing yesterday. So like yesterday, what I was saying is that if you had like a vector and you had a matrix, like the matrix, you can use it to produce a new vector. The new vector that you get is this one. I'm just going to, so this is like, again, this was like the old vector. And this is like, this was the new vector, which is called A times V, that's correct. So A times V was this new vector. What I'm trying to say now is that now with the help of the dot product, oops, I should use a different color here. With the help of the dot product, it is easier to identify or memorize what these entries are. So if you think about it, how is the first vector of the matrix obtained from a dot product? Can anyone see that? Because this should hopefully remind you of a dot product, right? It is two numbers being multiplied and then added, right? So what is that does this look like a dot product to you? Anyone wants to try to think, I'm using the colors in a way that's hopefully a convenient thing to suggest what the formula should be. But you know, if you think about the first row of the matrix as a vector, which you can, the important thing is that this vector has two entries, right? 1 and 2. So you can still do the dot product between this and this. Like the important thing with the dot product is not so much that I'm writing them vertically or horizontally, it's more that the number of entries is the same. So, you know, if you do the dot product between AV and XY, you get AX because this is first entry with first entry, and then BY because this is second entry with second entry. Is that making sense?
Yeah.
So these, like what I'm saying is that this is really the dot product between the first row of the matrix with the vector V. And what should I put here? So the second entry is going to be the dot product between the second row of the matrix and the vector V. Is that okay? Are there any questions about this? You can think about it in that way if you know. I mean, right, like there's two ways to think about this. Like if you wanted to insist on, right, like if you wanted to insist on putting like the two vectors like vertically, yeah, you can think that first you take the first row and make it a vertical vector, right? You kind of turn it into AV, and then you do that product with X and Y, right? But I think that's fine, that works, but it's a little bit of an overkill in the sense like the important, like, you know, it's kind of, you won't get confused in practice because the important thing is like this vector still has like a first entry and a second entry. And this vector has like a first entry and a second entry. So it says first with first and second with second. It doesn't matter too much that, you know, whether the first, like the entries are organized horizontally or vertically. The important thing is that you can, like, you know, if you like these computer programs, like it is like a list of numbers, right? The important thing for the computer would be that you are telling the computer, this is the first number in the list, the second number in the list, the third number in the list. It matters less whether like you visually stack them. Right, because they have the same size. So what I'm trying to say is that it is unambiguous, right? Like this row has two entries, right? That's unambiguous. So if you just read it from left to right, like it's clear that this is the first one and this is the second one. And it like this has two entries, so it's clear that, I mean, if you read it in the natural order, which is top to bottom, then it's also clear that this is the first entry and the second entry. So I'm just saying that the dot product, you can think of it as like you can do it like, you know, what I'm saying is like if you have something like this, like the only thing is that if you write the vector horizontally, you do have to put like a comma so that you don't confuse it, so that it's clear that it has two entries. But what I'm saying is that if you have something like this, and I ask you for the dot product, I mean, this is kind of clearly like first entry with first entry. You know what I mean? It shouldn't create too much of a confusion. Maybe I could have started there like anyways, but what I'm trying to say is that the dot product is 1 times 3 plus 3 times 5. Is that making sense? Like the important thing is that you can't, in both cases, you can talk about first entry, second entry of the vector in a kind of like clear way. So it doesn't matter too, of course, like if you wanted to insist on it, you could like just force this vector to turn this vector vertically, you know, first. So you can do that if you really want. If you have like a desire to always work with the vectors vertically, you can like, you know, just rotate it so that it's vertical. But I'm just saying like I mean, for practical purposes, like you kind of do these operations in your head and you'll see it won't cause too much of a confusion. Is that making sense? So for example, like let's do some examples, but I'm just saying this is like a very convenient way to remember like the the operation of a matrix with a vector. Okay. So here's some examples, and then I can give you one for you to think about as well. So here's an example. Let's say that the matrix had been like 1, 2, 3, 4, and the vector had been 1, -1, just to say something silly. So what am I talking about when I mean AV? I mean like like it really means what the matrix, it means like what is this matrix going to do to this vector? But now we do have like a more useful way to memorize that. What this means, like now the way we have to think of, we have the new way we have to think about, we have for thinking about this is that you take the first row, you take the first row of the matrix with the vector itself. Okay. So let me put like a different color here. So you take the first row, which is the vector 1, 2, and just take the dot product with the vector that you were given. So 1, -1. Again, it doesn't matter that one is vertical, the other is horizontal. Like that really doesn't create much of a confusion. That's going to be the first entry of the vector. And then you take the second row of the matrix with the same vector that you were given. So you put it like as 3, 4, 1, -1. And that gives you what? The first entry will be 1 - 2, right? When you do the dot product, you do this with this and this with this. And the bottom, it would be this with this. So that gives you 3. And then, sorry, this was a -1. So just to emphasize. And then this one with this one is -4. Right, so you get -1, -1. Is that making sense? So you see, it's like way easier to memorize this operation if you have the dot product. It's very easy. You just take the rows of the matrix and dot them with the vector you were given. In fact, you can do this, and this doesn't work just in the case of 2 by 2. So just to get ahead of ourselves a little bit, but it can be useful to try it out in other cases. So the thing works, the same idea works if the matrix has a bigger size. So just to give you an example, let's say I gave you like 1, 0, 2, -1, 2, 3, 1, 1, 1. Let's say I give you this matrix. No, the idea is that you will upload your solutions to Canvas. Yeah. I was going to explain that tomorrow, but yeah, it's just like you take the quiz on Respondas, and after you're done, you just upload your solutions. So it's kind of like but you have a separate time for doing the upload from the quiz. Yeah, I usually give people like 15 minutes to upload the solutions. I mean, that's more than enough time, especially at the beginning, because the questions are very short, but yeah, that's not part of the quiz time, so. Okay. So imagine that, like, again, like we haven't done this before, but like what I'm trying to say is that it is going to be the same idea. Okay. So what is A, B going to be? And I'll give you like a second to think about it, but think about it being dot product between first row and the vector, second row and the vector, and third row and the vector. So try to work it out. And maybe I'll give you 2 minutes to work it out and you can tell me what entries you get and then we can do it together. Okay, good. That's what you found. Let me bring some coffee. Okay, so is that what everyone got? Let's see. So it is like the same. So you get 1, 0, 2 dotted with 2. Maybe I need more space here. And you can even see that it is kind of like for writing it out, it's more convenient to even write everything like horizontally sometimes. So, you know, you don't like, there's nothing bad that will happen if you write the vector b in that way as well. If you wanted to save yourself some space, like just in terms of what you're going to put in, like in here, like in practice, like you don't need, I'm not even expecting you to write this out. Like you can just like, once you have done this many times, you can just immediately compute the answer, right? It's not like that you need this intermediate step. Like the first few times it's kind of useful. But you know, like it is just like a bunch of multiplication. So it's not like, so yeah, it gives you what 1 times 2 is 2. And well, the other one is going to be 0 and then 6. Right, it says 5, 4, yes, yeah, I think so. And then it's -2, -2, right? Plus what, 9? Yeah, and then 2 minus 1 plus 3. Is that what everyone is getting? So you do have to be careful because there's so many multiplications involved and additions that it is easy to get like a typo because you just do this quickly. But it's not that like the operations themselves are complicated. It's just like there's so many that just increases the chances that you make a mistake. You know what I mean? Right. That's going to be correct. So I may say I can say this in a second. So it's 8, 5, and 4. Is that okay? So let me just first check that this is okay with everyone. So is it how I'm getting this vector? Okay, is that making sense? So yeah, just to answer the question on the chat, as a remark, and again, I'll give you like the rules on when the multiplications can occur. But yeah, if I can give you the same matrix as before, like or like a 3 by 3 matrix, like that's going to be called like 3 by 3, but 1, 0, 2 minus 1, 2, 3, and 1, 1, 1. And let's say I got given you just a vector like this, right? These you cannot, I mean, again, I'll give you the rules in a couple of minutes, but this operation you cannot do, can't be done, right? Because since we need like, you know, we need 3 entries because like the size of the entries of the rows must match the entries of the vector. Is that making sense? Since otherwise you would not be able to do the dot product business. Since the entries of the rows, the number of entries of the rows must actually coincide with the entries of the vector. Is that making sense? So here our rows have 3 entries and the vector had 2, so there's no way to do the dot product operation between them. So like, again, I'll give you like a couple of rules on how to define this in general, but you would just say that in this case, you cannot like define this times this. Okay. Is that making sense? And now comes like the fun part, which gets us back to what we ended up talking about yesterday, which is how to do the matrix multiplication. So now we can take advantage of the dot product to do the matrix multiplication. So let me get that. Let's try to work that out. So I'm going to give you 2 matrices, okay? I'll explain what I mean by this. So I give you 2 matrices. Let's start with something like 1, 2, 3. 1, 2, 3, 3. Okay, I'm giving you these 2 matrices, and I'm about to explain to you what we want this multiplication to be. And we're actually going to do the most straightforward thing, and that's actually going to coincide with the formula I gave you last time. But it's kind of useful to just understand it from scratch, like what we're about to do. So in this case, like the idea, if you look about it, like when we had like a single matrix and a vector, we would just do the dot products operations, right? So that's essentially what we're going to continue doing. So we're going to think of the second matrix as 2 vectors. That's basically the strategy. So if you thought about it as 2 vectors, let me try to put some colors here to make this easier to understand. So if you thought about it as now think of this matrix as 2 vertical vectors. So how would you like just ignore this vector for now? So you just have like this matrix with this vector. So what would you get? You would get 1, -1 dot 1, 3, and then 2, 3 dot 1, 3. Is that making sense? So that's what you would get. That's what you would get if there were no second column, right? So ignoring the second column, that's what you would have obtained in this operation. Is that making sense? And then you just pretend, and now what you do to fill this up is just pretend that now the first column doesn't exist, and then you have this matrix with the second column, and you do exactly the same. Is that okay?
Professor, I want to confirm that so use the -1 times 1, 3, because 1, 3 stand for the x, y.
Correct.
And then 2, 3, you mean this, I mean the second box, 2, 3 is stand for x2 and the x and the y2, right?
Right. So you could, I mean, if you want, you could call them the first, like the 1, 3. You could call it x1 and y1 if you prefer.
Okay,
What I'm trying to say is, it's like the philosophy when taking two matrices is to consider of the first one is as a matrix, right? Think of the first one as an honest matrix, and think of the second one as two separate vectors, right? So that you can do
how
matrix
did
with.
you know when is which one is a matrix?
This like I mean, it just has to be done this way so that it will match. Like if you remember, long time ago, I got giving you this formula, right?
Yes,
That the only way for that formula to agree with what I'm doing. I mean, if I want this to agree with that previous formula, I have to think about it that way. So it's always like the left one most, the one that's regarded as the matrix. I'll do it in the
Oh,
opposite order.
okay.
So it's not like ambiguous. Like it's just always you know, this is the one that is always thought as a matrix, and this is the one that's thought as two vectors.
Okay, gotcha.
So like yeah. So it's this one is thought as a matrix. Like maybe I should put it thought of as a single matrix, right? And this one is thought of as two vectors. And that's
Gotcha.
like you have to do it that way so that it coincides basically with the formula I had written yesterday.
Mm,
But it's yeah, once you remember that, then really it's not like it's not it won't cause like complications, but yeah, no, like that's always like the standard convention, like when reading this. So what do you get here? You get what's the first dot product is 1 minus 3, right? So this one is 1 minus 3. This one is what? 2 plus 9, right? This one is 2 minus 3. By the way, let me know if I make a mistake, because this is where, like, there's so many multiplications happening at the same time that it's easy to make a mistake. And then this dot product is 4 plus 9, right? Is that okay? Is that what everyone else found as well? And so what do you get? You get minus 2, you get 11, you get -1, and then you get 13, right? So you would say that the multiplication between these two matrices is that matrix that you just see there. Okay? Is that making sense so far, so good? But now comes the fun part, because now what if you had changed the order in which the matrices appear? So now let's think about the different order of the matrices, right? What if you reverse what if you put them in the opposite order, right? So it's like 1, 2, 3, 3. And now it's 1, -1, 2, 3. Okay, so the thing is that now the convention is the same. So you really think of the first one that appears as the matrix, and now you think of this as two vectors. So you see, like, you still, like, you kind of apply the same logic, but now each matrix is being studied in a different way. So now, just to now, this is the one that's getting split, like, this is the one that you have to think about with the rows. And this one you think about in terms of the columns. So you get 1, 2 dot 1, 2, and then you get 3, 3 dot 1, 2, and then you get 1, 2, dot, negative 1, 3. And then you get 3, 3, negative 1, 3. Is that making sense? So again, like it's the thing is like this one is the one that's always regarded as a matrix. So it's now matrix with this vector, right? Matrix with this vector, so that's why I'm getting these entries, and then it's matrix with this other vector, and that's why I'm getting these entries. Is that okay? And so you end up getting for the first entry now you get 1 plus 4, right? Here you get 3 plus 6, correct? Then here you get minus 1 plus 6. And here you get minus 3 plus 9, right? Is that making sense? And so what does that give you? It gives you 6, 9, 5, 6. Is that, yeah. So that's what you would find if you do it this way. Is that making sense? Which, by the way, notice that it is different from what we found before, but that kind of makes sense because like you're changing your mind depending on in which order you place them. One of the matrices is being thought of as an actual matrix, and the other one is being thought of as a bunch of as a bunch of vectors. So of course, like it would make sense from that point of view that for the answers to be the same. For the answers to be different because you're changing your mind. Like the treatment that each matrix receives does depend on the position on which it is written. You see, so and this is different from the previous one. Different from the product in the opposite order. Is that okay? So any questions about this so far so good? So again, it is very easy to memorize. I mean, with the help of the dot product, this is a lot easier to do in practice. So it is like a better way to do it than like just like having like a crazy formula, which is what I wrote last time. So this is kind of like the way in which I expect you to think about these operations. If that makes sense. Okay, so let's take a so far if you notice, like I have been focusing on matrices that have 2 rows, 2 columns. They're called 2 by 2 matrices. So what we're going to do after, let's take like a 5-minute break. So after the break, what I'll do is like how to do this like in more general situations, not just when the matrices have like are 2 by 2. So I'll start giving you like the formula for the general situation, and you'll see. I mean, it's more or less essentially what we have been doing, but it's still. But it's better to start with the 2 by 2 case. So let's take just like a quick 5-minute break, and then we come back. I'll explain that to you. Okay, so let's now do the same kind of thing, but in the more general case. So in order to do that, I have to tell you some notation conventions when referring to the size of a matrix. So let's talk about that first for a bit, and then I can tell you how to multiply matrices of different size. So here's like the size notation of the matrix. So if you have a matrix A, A has size m by n. Okay, if it has m rows and n columns. Okay, so again, it's just easier to write this in practice so that you, with some examples, it becomes very clear what this means. So let's start with the easier one, which is like if I wrote something like this, right? So that is, you know, 2 rows and 2 columns. So you would say that this is like a matrix of size 2 by 2. But now if I wrote something like this, right? How many rows does it have? It has 1, 2 rows, but then how many columns it has is 1, 2, 3. So it's now 2 by 3. So you would call this a 2 by 3 matrix. And if you have something like 1, 0, 1. Well, let's do something more like exciting. Yeah. Let's do 1, 1, 0, 1. And then -1, 1, 2, 1, and 1, 1, 1, 1. So what's the size? What would be the size for this one? Well, it always is the rows first, right? Yeah. It's always the rows first. So you would call this a 4 by 3 matrix. So it's just good. It's just, I mean, you know, it gets a little bit, takes some time to get used to it, but it's always count the rows first. Okay. So again, if you write A, so if you write something like A m by n, this refers to rows, number of rows, and this refers to number of columns. Okay, so it's always rows, columns, rows, columns, rows, columns. Is that okay? Is that making sense? And so, like what we were working with was like a 2 by like most of the examples I have done so far were like 2 by 2 matrices, because that's kind of like the easiest thing to start with. But you see, like later on, we will have some interest in matrices which are a little bit more complicated. So how many entries? Here's another thing that's like a simple counting, but it's kind of useful to notice. So notice if you have a matrix of size m by n, how many entries does it have? How many numbers are inside the matrix? Yeah, so the name is not like complete nonsense, right? Like it has m times n entries, right? So that's why the notation makes sense, because it reminds you of like, it does remind you of the number of entries inside the matrix. So for example, 2 by 2 has 4 entries, 2 by 3 has 6 entries, 4 by 3 has 12 entries, you see? So it's like, that's like a reason why the convention is useful. Because of that, I mean, because it reminds you of how many entries you should put inside the matrix. So it involves like right, like the number of entries is multiplied, right? So that's why you have, even when you have a few rows and few columns, you could have tons of matrix and tons of entries because you're multiplying the numbers. And just as an observation, which is kind of useful sometimes. So an observation. You can think, if you wanted to, as a vector, as a special kind of as a special type of matrix. So you can think of a vector as a special kind of matrix. It's sometimes convenient to have this perspective as a special type of matrix. Because, like, say, if I had like this vector, if I had like a vector like this or a vector like this, like, if you thought about it as a matrix, right? What would be the size of this matrix if you thought this is a matrix? Again, count number of rows first and then columns, right? So how many rows does this one have? It's a 2 by 1. Good. It would be a 2 by 1 matrix. That's why these vectors sometimes are called column vectors, because it just has one column. And how many? What would this one be? It would be a 3 by 1 matrix, right? I mean, so it's something you can do. It's useful to think about it that way as well. So this is why these vectors sometimes are called column vectors, because they just literally represent a column. They're just like a single column. That's a special kind of matrix with a single column. So that's kind of nice to see as well. Okay, so far so good. Questions about this up to this point? Okay, so now we're getting to something cool, which is let me start with an example before I give you the general formula. So now we can talk about multiplying matrices of different size. So imagine, let me start with something. 2 by 2. Yeah, I'll start with something smaller. So imagine that, okay, here, like, we're kind of experimenting a little bit. Just to see if what I have been saying so far makes sense. So first of all, someone tell me the size of this matrix. So what's the size of this matrix? It's a 3 by 2 matrix, correct? Good. Is that making sense with everyone? Because it has 3 rows. And 2 columns, right? And how about this one? What would this size be? It would be 2 by 3. Good. So I'm going to claim that we should be able to multiply these two matrices, and you'll see why in a moment. But the way, if you follow the instructions that I gave you before, the instructions were like, think of this as a matrix, right? Think of this as a matrix, and this as and the first column just as a single vector, right? So the question is, would you be able to do this matrix multiplication times this vector? And the answer should be yes, because like the rows have 2 entries and the vector has 2 entries, right? So if you just follow the logic that I gave you before, right? Let me just put this in color, one color. You would do 1, -1, dot 1, 2, 0, 1, dot 1, 2, and then 1, 0, dot 1, 2. Is that making sense? So I'm doing the first row with this column, the second row with this column, and the third row with this column, and I'm putting all the answers here. Is that okay? Is that kind of making sense?
Yes.
And then what you would do is just move to the second column and pretend again that that's a single vector. You ignore the rest of the matrix, and then you would proceed in the same way. So you can give this a different color. So now you would do, let me copy these again. So you would get that. And then you kind of do the same. You pretend that this is like the only column vector that you have. And so since the rows have 2 entries, then you can do the dot products. So you would put, oops, I'm running quickly out of space, but let me see if I can write this down. And then you would have that. Is that making sense? And so how many entries are we putting inside this array? How many entries are we getting here? Maybe I should do the dot products first, because then it's easier to see how many entries we get. So the first dot product would be 1 minus 2. Let me do this in red so that so it's 1 minus 2, then 0 plus 2, and then 1 plus 0. Then you get 0 minus 1, and then 0 plus 1, and then 0 plus 0, right? And then you're getting minus 1, minus 2. And then you're getting 0 plus 2. Again, if there's any mistakes, just let me know, because it can be easy to make a typo here. Oh, you get. minus 1, 2, 1. Minus 1, 1, 0. Minus 3 to -1. And so that's what we would get. Is that making sense? So what's the size of this matrix? It's 3 by 3, and you'll see, and I'll tell you the formula in a second. The fact that this 3 by 3, the first 3 will come from this 3, and the second 3 will come from this 3. Okay, so that's how we will, in general, determine the size of those matrices. But now, let me put it in a different order. So imagine like I had written the matrices in the opposite order. So now it's 1, 0, -1, 1, 0, -1, 2, 1, 2, right? And then 1, -1, 0, 1, 1, 0. Okay. Good. Now, what are the sizes here? The sizes are still the same, right? It's 2 by 3. And what? 3 by 2, correct? And so what should the matrix be in this case? Well, it is the same philosophy, where think of this as only a single column. So I'm not going to do the dot products between this and this. And then think of this as a single column, and I'm going to do the same. So I'm going to do 1, 0, -1, dot, and then 2, 1, 2, dot with this column. So what am I getting? I'm getting 1 plus 0 minus 1, and then I'm getting 2 plus 0 plus 2, and I'm getting here minus 1 plus 0 plus 0, minus 2 plus 1 plus 0, right? And so what am I getting here? I'm getting, again, let me know if there are any typos, but getting here minus 1. Is that making sense? And what's the size of this matrix? It's 2 by 2. Good, 2 by 2. And again, what I'm going to explain to you in a second is that this 2 comes from the first 2, and this second 2 comes from this 2. Okay, but like what I'm trying to emphasize here at the first of all is that now, before, like when we had two by 2 matrices, like the order matters, right? Like the order matter. Now this is even worse because even the size of the matrix could be different, right? So now changing the order in which the matrices appear can change their size, like of the resulting matrix. So see, it's even worse than the case when both had the same size, right? Because when at least both had the same size, I mean, you would get like a matrix of the original size. But now, when the matrices are of different sizes, like the resulting matrix can just you know, one can be like 2 by 2 and the other one could be 3 by 3. So there's even like less of a chance of a comparison, right? And it can be even worse than that. So now let me say that. So now the sizes even can be different. So now the resulting matrices can be of different sizes. But it is again it can even be worse than that, because sometimes you can only do the multiplication in one of the two orders. So in this example, both orders work. It's just that they give you different matrices, different size matrices, which is fine. But it can be a situation where like only one of the two orders could work. So, but there are even cases. So just to give you an example of that, so let's say here's an example of this. Let's say I had given you 1, 0, -1, 2, 1, 2. I think this one is the same from before. This is a 2 by 3 matrix, right? And now I'll give you 1, 0, 1, -1, 1, 0, 0, 0, 1, 0, 0, 1. Okay. So let me so what is this matrix? It's a 3 by 4 matrix, right? So what is happening here? Like again, I think you're getting like the idea of how the dot products, like the entries are computed. So I'm doing the dot product between. I'm going to do first the dot product between this and this. So what is that dot product? Is 1 plus 0 minus 1. Then put in the dot product between this and this. So that gives me what? 2 plus 0 plus 2. So that goes first. Then let's move to the second column. So when you do this one with this one, you get what? -1 plus 0 plus 0, right? And how about this one with this one? You get -2 plus 1 plus 0, right? Now, what do you get on the third column? You get, this one is easier. It's like, it's 0, 0, -1. And this one is 0, 0 plus 2. And the last one, let's put the last one here. The last one is this with this. It gives you what? It gives you 0, 0, -1. And then it gives you this with this is 0, 0, 2. Is that making sense? Are there any questions about how I found these numbers? And so what do we end up getting here? We end up getting 0, 4. We get -1, -1. Then you get -1, 2. And then you get -1, 2. I think that should be the answer. So what is this? The size of this matrix is 2 by 4, right? And again, the fact that it's 2 by 4 just comes from the fact that there's a 2 here and there's a 4 here. Okay, but okay, maybe I should stop here. Is that making sense so far? So good. But now, what would have been, what if you had tried a different order? So this is still 3 by 4, but now this is 2 by 3. And what anyone can you see the problem that happens now if you try to multiply this together? Is that clear? What's the problem now? The sizes do not match, right? So now you cannot do the dot products. So this cannot be done because the sizes are incorrect. Is that making sense? Like, for example, this one could not be multiplied with this one, like, because it has 4 entries with 2 entries, and you cannot do the dot product between 4 and 2. And so, and that's more, oops, sorry. That's basically what can go wrong. So I can, now I can give you the, like, the idea of, like, of what, like, the result is in general. So in general, if you have a matrix, two matrices A and B can be multiplied. A times B. This can be multiplied. Let's say that A was like n by n. Right, exactly. Yes. So what I'm saying is that if you want to multiply two matrices like this, you first need the number of columns of the first one to coincide with the number of columns of the second. Sorry, the number of columns of the first one to coincide with the number of rows of the second. So that has to be like this. So the two numbers in the middle must coincide. So what this means is that number of columns of A must be the same as the number of columns of B. Sorry, number of rows of B. Oops. It's better to say it in terms of the numbers. So the interior numbers, they must match. If they don't match, you cannot do the multiplication. The multiplication is not defined. So if this match, then you can do the multiplication. And the multiplication will have size m by l. And the resulting matrix. Correct. You cannot do 4 2 with 3 1. Exactly. Yes. And that kind of matches with what we were doing in the previous examples. Well, let me give you a second to copy this. So and then I'll show you.
Professor, could you explain one more time, like what is how the columns of the A equal to row?
Oh,
please?
this is a condition for the multiplication to take place. So what I'm saying is that the multiplication can only take place if the interior numbers, when you write out the sizes, the interior numbers must match. So for example, here,
Yeah.
just to get back here, like these two match, so you could do the multiplication.
Oh, okay.
But here, these two did not match, so that's why we couldn't do the multiplication. Is that making sense?
Yes. Touch.
So that's what this is what this means, like the stuff in pink. I'm just writing it out in words, but this is what this is saying. So like
Gotcha.
basically this is why it's useful to write out the sizes, especially at the beginning when you're getting used to this. When you write out the sizes in this way, you can just check by verifying whether the interior numbers match. And if they match, then the size of the new matrix will be this size times this other size, which is what we got here. So for example, when we did this here, like you got 2 by 4, and it doesn't change. I mean, it appears in the same order. It's very, that's why it's convenient to write it the way it's written, or the sizes of the matrix.
Makes
Is
sense.
that making sense?
Thank-
Yeah, sure. So I mean, that's why in general, that's why you cannot just put B then A, because you have to check whether the sizes agree. So yeah, like this is like I think just to do this practice, we can do problem 9 on the PDF. That's one of the problems I had recommended for the quiz. So let's just work it out in the remaining minutes that we have, and then we can end the class. So here's like the problem 49 from the PDF. It's just like it's just a couple of questions about sizes. Well, that's weird because it is the same link as a Canvas site. I'm not sure. You mean yesterday? Oh, it's just that I had said that I usually will come. I had to close the meeting because to store the video, but to save the video to my computer. But then I would show up to the meeting again. Maybe that's what happened. Maybe you just showed up before I logged back in. Is that I log off and then I log in again? But yeah, you can. Will be for the office hours today. Yeah, it could, but that could have been the issue. So the first question is like, if A is a square matrix. Sorry, if A squared is defined. So this is like a true false question. If A squared is defined, A squared means A times A, I should say. Like, I mean, it's like, if A is a matrix and A squared makes sense, then A has the same number of rows and columns. Okay. Yeah, let's work it out. So here's how you should think about these problems. I don't know the size of A. So since you don't know the size of A, call A an M by N matrix, right? Because we don't know what that size is. So you just call it M by N. And then what is A squared? A squared is A times A. So you would have M by N times M by N, right? And so what I was saying is that the only way for the multiplication to make sense is that for the interior numbers to coincide, right? We need these two to coincide. So this must coincide. and that gives you that n equals m. Is that making sense? So if n equals m, that means that it is like the same number of rows as columns. So it is a square matrix. Correct. That's another way to say it. You can only take the square of a square matrix. Yes. Good. That's it sounds a little bit confusing, but yes, that's a way to that's the correct way. Yeah, that's one way to put it. Is that okay?
Professor, what
Mhm.
about a with the 3 powers? Or with the third
Oh,
power?
okay. That's a good question. So right, what would be a cube? Like that's kind of like a squared a, right? And so for this one to make sense already, I mean, since you have already an a squared, that only makes sense when a has a, you know, that's the same number of rows and columns. And once that happens, you can keep multiplying it with itself. So
Mhm.
this also works only when m equals n also. So like once you have like any power of a, like a squared, a cubed, a fourth, a to the fifth, they do require like the same number of rows as columns. Is that making sense?
No, not really. 'Cause-
So the thing is like this already requires a squared to make sense, right?
Yeah,
And for a squared to make sense, you must have the same number of rows and columns. So this already needs, this one already needs.
oh, you mean even in the a square, when you have the m equals m, so after that, we can just
Right.
use
Yeah. After
to
once
compare the a square and a.
right. Once you know
Oh.
once you know that, you can just keep multiplying it with itself because it has the same number of rows and columns. So
Okay.
is that better now?
Yeah, thank you.
Yeah. So and but by the way, all of these powers end up having the same size as the original matrix. So like if a maybe I should write that as well. If a is m by m, then a squared, a cube, a to the 4, etc. is of the same size m by m. Is that okay?
Yeah.
And then the next one in the problem was that, okay, now here you have, this is one that's part 2. Now you have the A and B. So now you have two matrices. For which AB and BA make sense. So does that mean that A and B are each square matrices? Are each
Professor,
Mhm.
I had a question. For
Yes.
these type of true and false questions, when it says does it mean A, B are square matrices, does it mean they have to be square matrices, or does it mean
Right,
they could be square matrix?
no, it means if they're forced to be square matrices, like if that forces them to, like if that's the only way for this to happen.
Oh, okay.
Yeah. So let's like again, is kind of, let's just work it out. I don't know what the sizes for A and B are, so let's call A m by n, right? And let's call B, you can call B P times Q. That kind of works if you want to give it 2 different letters. So what does AB require? AB requires AB would be m by n and B P times Q, right? And that would require P to be equals to n, right? This forces this forces N and P to be the same, right? And what about B times A? So what if you do B times A? And then N by N, right? If you write B times
Equal to
that forces Q to equal M, right? So you can write like the matrices as M by N, and B is like, B was P times Q, but P is N, right? P is N, and Q is M, right? But notice that that doesn't, like, from there, besides that, we don't have any other conditions, right? So that doesn't mean that still doesn't force like M and N to be the same, right? Doesn't force M and N to equal each other. So in fact, you could take, just to see that this works, like you could take something like this, which is 2 by 3, and this, which is 3 by 2. Sorry, 3 by 2. So if you look at something like this, you'll check that either order works here. Either AB and BA works. So it gives you like an example where you didn't need to have like the same, it wasn't necessary for like M and N to be the equal. Is that making sense?
Yeah.
And then in this case, like notice that if that happens, then what would be AB? AB would be MN times NM. So this one gives you a size M by M matrix. Like the product, and BA would have been like NM times MN, and that would have been like an N by N matrix. So in this case, these two matrices are square. Like, so in this case, like this is part C that's asking whether the two matrices were square or not. So yeah, the two.
Professor,
Yes.
why do they have to be square? Because like, say if we had A equal to 4x, like times 3, or if like the size was 4x3 and then the B was a 3x2, you would have a matrix of 4x2 as a size. And then that
So-
would mean that AB wouldn't be square, right?
So you're saying A 4 3.
And then
And
B was
B-
3 2.
Right, but the problem, okay, so I agree that this one would be 4 times 2, right?
Mhm.
But the problem is asking you for both in both orders to make sense. So,
Oh, so okay.
right, you know what I mean? So if you only care about for one of the two orders to make sense, then that would be enough. So, but yeah, like in this problem, both AB and BA make sense. So that's what's forcing them to end up being squared matrices. Is that making sense?
Mhm.
And then part D, well, requires talking about the identity matrix, which I haven't done. So I'll do that. I mean, so you can ignore that one tomorrow, part D for now. So I won't, because I didn't have a chance to tell you what the identity matrix is. So, but yeah, that's kind of how you play with the sizes of the matrices. So yeah, I think it's probably a good place to end. So as I said, I'll just download the video to my computer, and I should join in like in 10 minutes back to this Canvas meeting. So I'll see if there are no more questions. I'll see you tomorrow. I mean, you can also, if you prefer, you can ask me right now what you wanted to ask me. Like, up to you. So for office hours, I mean, I can just pause the video. Like
So
in 10 minutes, or if you want, you can also ask me now.
I had a quick question about
Mhm.
problem 47.
Yeah, let me check.
So I
yes.
kind of understand that very last line where it says same as rotating by negative theta, that is r 2 pi minus theta equals to r theta.
Oh, so
Would
I
that be
should
r
have put.
negative theta?
Yeah, this was a typo. It should have been r minus theta. Here, you mean?
Mhm.
Yeah, it was a typo. Sorry. I will fix that. Yes.
Oh, no worries,
Um,
thank you.
Yeah. Because like the idea is like to get back to where you started. Yeah, you just need to. There are two ways to think about it. Like you either do 2 pi minus theta to do like a 360 rotation, right? That
Mhm.
puts you in the same place, or you rotate clockwise. But rotating clockwise is kind of like doing an angle of minus theta. But yeah, this one should. I'll fix it. Thanks.
Mhm.
Is that the only one that you wanted to ask me?
Yeah, that's it.
Okay. Okay.
Oh, Professor, for the
Yes.
office hour, where is the link? Because I didn't see.
It's the same link as again, it's what I was saying. It is the same link. It's just that you usually log off to just save the computer to my computer, but it depends. Like you can ask me now if you want also.
Okay.
I can just pause the video. I mean, or I can just keep it going, like because then I can answer these. Yeah. Was there? Yes. What do you want to ask me?
Gotcha.
Anyone else? Good. Bye.
Oh, actually, for the
Mhm.
problem 19, sorry, I was just
19.
looking at it. I don't know if we went over in class, but you say like the matrix will be commutable, right? So like AB will then equal also the BA. It would be both.
Right. I didn't. Yeah. So I guess since I didn't use that word, I wouldn't ask it for the quiz. You can. Yeah, because I still didn't explain what commutes means, but commutes means that A times B is the same as B times A. Correct.
Oh, so like if it's the same property as like the commutative property, would there be like a property such as associative and distributive property too later on?
There isn't. Okay. Yeah. So commutative. I mean, right. So do we have? So commutative would mean that AB equals B. I'm writing it on the chat. Commutative means that A times B is the same as B times A. That doesn't
Mhm.
happen all the time, right? So, it's kind of like I think that sometimes happens, sometimes doesn't happen. The thing that always will happen, I have to give you those properties tomorrow, is that it is always associative. So, like like A B C is the same as A B C. Like if you see it in the chat as I'm writing it. So the parentheses
okay.
the parentheses can be moved around every single time.
Mhm.
And you can also distribute like A plus times B plus C is AB plus AC. That also does work.
Oh, so it's also okay. I see.
So like that, so this you can distribute, you can do the associative property always. What is not always true is that you can move the
Do
order of the
commutative.
multiplication.
Oh, I
Yeah.
see.
But so in this problem, but again, since I didn't use that terminology, I wouldn't include it on the quiz because I didn't define commute yet. But I was asking, find all the matrices that when you multiply them with 1, 1, 1, 1, it doesn't matter the order. You see, so
So for the associative one, if A was like a 3x4 matrix and then BC ended up being like a 2x2, how would it be?
no. So it like the thing is like here, like when I say associative, it's implicitly. I mean, it can only work under the. I mean, it's let's just say like this: if the orders makes like if the multiplication sizes are correct, then
Mhm.
it's associative. But you kind of have to put the hypothesis that to start with the product already makes sense. So
Oh, like a precondition, like all the matrices
right,
have
like
that
a
same stuff.
precondition, right. It's kind of saying if the expression makes sense to begin with, then it's associative. But of
Mhm.
course, if the expression didn't make sense, then the question wouldn't even be well defined, right? Like for example, when I'm saying that AB equals is not always equal to BA, like that's only interesting to check in cases where like in both orders you can do the multiplication, right? Because if like there are orders in which you cannot even do them, then it wouldn't be like a property you would care to check about. Is that making sense?
That makes sense.
So yeah. So it's kind of like right as a precondition. If all the sizes work the way they're supposed to, then it will be associative.
Got it.
Yeah. Otherwise, yeah, you could not even state the property to begin with. But okay.
All right. Thank you. Have a nice day.
You too. Were you going to ask me something, or you want to wait until? Okay, let me stop sharing. Just in case I'll log in back in a couple of minutes. I'm just going to save the video to my computer.